Okay, so today we will talk about this concept of broken symmetry, which was the puzzle that I posed in the Ising model. And I will do a very brief intro to renormalization group. That's a complicated topic. I will give you a basic flavor for what it's about. I have posted an article on the class website that has a very nice description from Leo Kadanoff on a bigger description of what it is really about. And you can keep reading more and more. There are lots and lots of textbooks on renormalization group. It's a nice concept. Oh, please submit your course evaluations, okay? So why should you submit your course evaluations? You should submit it because it's useful. To me, it's useful to the university to see that students care about StatMech. It helps the higher ups see that, oh, the StatMech seems kind of students are interested in it. Maybe we should hire more people, things like that. So they look at things like this. They see that if the course evaluation feedback is like less than 20% or 30%, they feel students don't care about this course. And then we are always on the chopping block. There are departments in the UK where universities in the UK where the whole chemistry department was shut down. Things happen. So please submit your course eval. And you can also send me feedback separately if you want, but So you should have received a link. It's due till next Friday. So I would really like to see at least 90%, ideally 100%. That is 100% number of students participating. So, okay, so today's topic is not on the exam, so thank you for coming, but it's still useful. You will hopefully appreciate what it is. On Tuesday, I will do a recap of the semester, okay? So it will be a quick class. If you have any questions, you can send to me on Slack, and we will do a big picture recap of what this course was all about, what are the main things that you should think about. So, try to join, and Thursday there won't be a class. So we were talking about our Ising model, and let's think about an Ising model with no external field. So if you don't have any external field, the energy of an Ising model in a given microstate is going to be looking at different spins, and maybe these are first neighbor spins, maybe these are more than first neighbor spins, I don't care, some spins. Almost certainly it's going to be I not equal to J. This term is exchange term, right? It never connects with the same spin. So we have something like this when H is equal to 0. So the simple observation you can make here is that if you wrote down a microstate where every spin was changed to the opposite of what it was. So maybe SI was +1, you make it -1, and maybe SJ was -1, you make it +1. So if you make every spin exactly opposite of what it was, so SI went to minus SI and SJ went to minus SJ, E nu does not change, right? Minus minus is 1, E nu does not change. And what is the probability so this is a microstate. So the top one is, for example, a microstate that looks like this, right? And the bottom one is a microstate which is going to look like this, right? You have just flipped everything exactly opposite. So the probability of both of these microstate is proportional to e to the power minus beta E nu, right? And since E nu is the same, probability is the same for both. We have a fundamental problem here, right? If you have any spin with a given magnetization, any configuration with a given magnetization, the equal and opposite magnetization will have the same probability, which means that if you average out the magnetization, it should be 0 at any temperature, irrespective of any interaction. And we know this is not true, right? When do you think this might be true? Can you think of a case where this might be true? Chocolate at stake. If you don't answer it, I will eat the chocolate. So don't get me fat. No, I'm not going to. I said any temperature. What is a physical scenario? You don't get chocolate for this. Where magnetization, average magnetization is 0 at any temperature. We saw a case.
If they, I don't know, they prefer to be anti-aligned.
No.
They're very statistic, but if you had like a frustrated magnetic
Oh, think simpler. No, that's terrible answer. Think simpler. We studied it. Go ahead, Aurelia. Yes. No. What is the physical setup? If they're all pointing in the same direction, then magnetization is not 0, then it's definitely non-zero. So what is a physical setup in which average magnetization is 0 at any temperature?
No spin, 1D.
1D, there you go. Here. Sorry. If it broke, you can have another one. 1D, we know in 1D, at any temperature more than 0. Why did he get it? That's not good. Does anyone agree with this, right? In 1D, this is true, right? In 1D, this will be, M will be 0 at exactly absolute 0. If you have the smallest possible temperature, the average fluctuations go to 0. The average magnetization goes to 0. But we clearly know this is not the case in high dimensions. There are finite temperatures at which magnetization can be non-zero, right? So how do we solve this puzzle? So in order to solve this, we are going to, and this is another reason why I want to talk about this, because it introduces a notion which is quite useful. So I will call it a solution, but it's really an intuitive idea of what's going on. And it gives you a sense of two concepts, broken symmetry, and it tells you about how systems become non-ergodic. So think if, even though our E nu was minus J summation Si Sj for I not equal to J, and we had the magnetic field 0, right? But imagine a case where there was a magnetic field. You apply a certain magnetic field, apply H, and gradually bring it to 0, okay? So the question is, how did you prepare your system, right? So you had a bunch of spins, and you had an external magnetic field which was very, very strong, and then you gradually start to tamp it down, okay? So what would happen if H tended to plus infinity? How would the spins look like for any value of J? Another chocolate steak. I will eat this one, I think. There's chocolate if you want to answer questions. So my question is, you have J finite, and the system could be 1D, 2D, 3D, whatever, and you had a very, very high magnetization which was positive. What would happen? Right.
All the line H.
Why?
Because that's direction of the magnetic field, right? So
Si will like to be the same direction as H. Here. Next question. If you raise your hand, you will get the first chance, Alex. I will try to have equal a priori probability of distributing chocolates. So Aiden and through Patrick, Nathan do not get everything. So the point here is, if you have a system and you apply a very, very high external magnetic field, all these spins will align in the direction of the magnetic field, right? Now you start to turn the magnetic field down, okay? What will happen now? That's what we need to think. So we apply this external magnetic field, and gradually we bring it to 0 plus, right? So we keep it slightly positive, but we keep decreasing it more and more and more and more, always staying slightly positive. So this is the experiment we want to describe. What's going to happen in this case?
depends on J.
Depends on J, of course. So let's say our J is equal to +1, okay? For simplicity, it will depend on J. So we are thinking about the case when J is equal to +1. So we are thinking about E nu is equal to minus, and actually it should be in the units of energy, right? So I'm being sloppy with units, but this is minus Si Sj, I not equal to J. And we have an external magnetic field that we gradually bring down to 0 plus. So if there was no external magnetic field, if we did not have this, then what is the ground state of this system at t equal to 0? All +1 or -1, right? However, if we have a slight external magnetic field, we realize that if the magnetic field is coming from +infinity, it will like to be towards +1, right? So you see, we are thinking about two regimes, right? When the H was +infinity, it likes to be everything along H. But when H goes to 0, so when H is equal to +infinity, all Si like to point in the direction of H, right? But when H is equal to 0, we know that Si is equal to plus minus, Si is equal to Sj is equal to +-1. Both are equally likely, right? So there is a contradiction. You see the contradiction, right? When H was +infinity, it can be, if H was positive, So H is positive, right? So this means Si must be equal to +1, right? But something happens when H becomes exactly 0. So this is what we need to understand, what's really going on here. In order to understand this, I'm going to do a little bit of math. I am going to think about the partition function of the system. So what is the partition function of the system? We are thinking about the canonical ensemble, right? So the partition function of the system is go to every microstate, do e to the power minus eta b nu, e to the power minus beta e nu, right? So I'm going to introduce a new quantity that we have not seen before. I'm going to call it the restricted partition function. And this is an interesting quantity, which you will see in different types of research areas. This one is called Q tilde, and it depends on M, okay? And this is defined in an interesting manner. So it goes over all the microstates. It again counts e to the power minus eta b, e to the power minus beta e nu for every microstate. However, here you have another function, which we call delta of m minus m nu, where delta of m minus m nu is equal to 1 if m nu is equal to m, 0 otherwise. So you see why this is called restricted partition function, right? So you are counting e to the power minus beta nu, but only for those magnetic states, only for those microstates where the magnetization for m here, just to remind you, is summation Si, right? Okay. So you want to look at a particular value of magnetization, right? So this is the first time you have seen something like this. So let me give you some intuition into this. So for example, I will write down what I wrote on the last page. So Q tilde of M is defined as going to every microstate and counting e to the power minus beta e nu in that microstate if the magnetization of that microstate is M. If the magnetization in that microstate is not M, then that state does not contribute. So for example, we can think about Q tilde of 0. What does Q tilde of 0 mean? Q tilde of 0 means that the sum of all spins is 0, right? How many microstates can contribute to sum of all spins equal to 0? Not chocolate coming. In a system where Si can be plus minus 1, okay, let's make it simpler. In a system where Si is equal to plus minus 1, how many microstates contribute to magnetization equal to N?
Is it N choose?
N is a large number, and you can't get a chocolate, sorry. In a system where spins can be plus minus 1 and you have N total spins, how many microstates contribute to magnetization N? What do you need every Si to be for magnetization? So remember, M is equal to summation Si, right? What values can, Nick, you tell me, what values can Si take? Plus minus 1. And I want the sum of Si's to be equal to N. How many Si's do I have? N. So how many combinations of Si can I have that their sum is equal to N? It's easier than you think. 1, there you go. Have a chocolate. All Si's have to be plus 1, right? Is that clear? So this comes from only one microstate, right? And for that special microstate, you will calculate e to the power minus beta nu. So this will be e to the power minus beta e nu when Si is equal to plus 1 for all I, right? Similarly, Q tilde of minus N comes from one microstate, right? Where everything is minus 1. Q tilde of 0, how about that now? You still think it's only one microstate? That will be a lot of microstates, right? You can have different combinations that they sum up to be 0, right? You can have plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus. You can have plus, minus, plus, minus, plus, minus, plus, minus. You can have all the left as plus, all the right as minus. You know, you can have so many different combinations. Maybe N choose to something, some large number, right? So Q tilde 0 will be many microstates where you have to go and sum e to the power minus beta nu, but every time you have to see whether that microstate has the net magnetization equal to 0, right? So why did I introduce this restricted partition function? Because now if I want to calculate the probability of finding the system with magnetization M, how do I get that probability from this Q tilde and Q? This is a 2 chocolate question. Huh? Why do you bring a log? You're in the right direction, but don't think about a log. It's simple. What did you have in your denominator?
Q.
And what do you have in your numerator? Q tilde of what?
M.
That's it. You get only 1 chocolate because you introduced the log. You don't need log. Partition function is already the probability, right? Log of partition function becomes free energy. We are talking about probability. So it's just going to be Q tilde of M divided by Q. Okay? Is that clear to everyone? Alex, can you explain it to everyone?
Yeah, basically we start with the same idea as our probability of microstate instead of one microstate bunch.
Yeah. So this is effectively going to every microstate, and we are calculating the ensemble average of this delta function. Okay, that's what we are doing. We are calculating the ensemble average of M minus M nu e to the power minus beta e nu divided by summation nu e to the power minus beta nu. So Q tilde M is like, so Q tilde M is proportional to the probability of finding the state in a given microstate, in a given magnetization, okay? So what we can do now is we can look at the log of Q tilde M. That's not going to be the probability, that's going to be a free energy, right? And we can call this with some name, we are going to call it A tilde of M. This A tilde of M is the free energy of the Ising model with magnetization M, okay? We also had Q in the denominator of the log, but free energy is a relative thing, right? We are interested in differences, right? So if I ask you, what is the relative free energy of the Ising model in 2 different magnetizations? One magnetization is M1, the other magnetization is M2. You can calculate the free energy difference between both of them by looking at minus KBT ln Q tilde of M1 minus plus KBT ln Q tilde of M2. Okay, so this is Chandler actually calls it potential of mean force of magnetization. Potential of mean force of magnetization. Okay, so this delta A, which is A tilde M1 minus A tilde M2, is the free energy difference between 2 configurations with magnetization M1 and magnetization M2. And physically, what does it mean? It really gives us the, yeah, it is just the free energy difference, right? So what is the meaning of free energy difference in thermodynamics? Free energy difference, anyone remember second law of thermodynamics when we did it? What does it say about work done with relative to free energy difference? Which one is higher? As per second law of thermodynamics, if you have to drive the system from point 1 to point 2, and the free energy difference between them is delta A, the work done to take the system from 1 to 2, is it going to be smaller than delta A, equal to delta A, or larger than delta A? No. Greater because of dissipation, right? You're going to lose something. It's like I want to run from point 1 to point 2, and I cannot convert all my, I will waste something, right? When I do it, I will sweat, something will happen, right? So W is always more than equal to delta A, right? Or delta F, whatever you have. This was our second law of thermodynamics. Don't forget that in your, now you're giving me ideas of how to make your final exam. There will be some thermodynamics. So del A tilde M1 minus A tilde M2. And when are these two equal? When is the work done equal to delta A? Reversible, right? Now, this gives the reversible work needed to change the system from magnetization M1 to M2. Okay, that's the idea. So let's try to plot how A tilde of M will look like. And here I'm going to just use intuition. I'm not going to go through the math. You can actually calculate it by looking at all the expressions, but hopefully you will see the intuitive sense. And this will finally solve our puzzle as to what's really going on at zero temperature. How do we have two degenerate states and what goes on? So I'm plotting here A tilde M versus M. How is it going to look like in 1D, where we have no phase transitions? Intuitively. No, in 1D, both are equally likely, right? It can be +1, it can be -1, it can just change its minds anytime it wants, right? So in 1D, it's going to look more or less like a flat line. Something like this, okay? And you will have some finite size effects. So then it will blow up like this. So Chandler draws a plot like this in 1D. So you can basically, so the idea being here that let's say in 1D, you prepared your system with a certain magnetization, right? So Swimin worked very, very hard and she prepared her system to have a magnetization of certain value. And then comes Alex and he says, yeah, I'm just gonna kick this one little spin and try to increase the magnetization. We know that it can happen. There is no cost, right? It can just happen. It can happen either way. He can push it to the right, he can push it to the left, right? There is no free energy cost. Any fluctuation is favored, right? So in 1D, it's going to look like this. In 2D, however, we know that there can be a phase transition, right? So in 2D, this plot starts to look like this. You still have finite size effects, and then a certain barrier appears in the middle. So the black one is 2D. Okay. Why did the barrier appear? What is the origin of this barrier? That you have a penalty, right? In 2D, when you create a domain, the energy cost of that domain increases with the surface area of the domain, right? Go ahead.
Is this average M or just M?
M. M is always defined as summation SI.
Okay.
Yeah, this is not a thermodynamic average. In 3D, what do we expect the barrier to do? Should it go lower? Should it go higher? Huh? There are only two answers, or it can stay the same. If you give me the correct answer and the correct intuitive reasoning, then you get a chocolate. What do you think? Why? So that's true, but think about critical temperature. What happens to the critical temperature as the dimensionality increases? It increases, right? So you can sustain a certain magnetization for a longer time. You know, that's the idea. So yeah, you can have a chocolate and just come and take it. So in 3D, it's going to look like this, okay? So this is 3D. This is 1D, and this is 2D. So this barrier that you have, E star increases with dimensionality. So let's just focus on any one of them, okay? Let's just focus on 2D on the next page. So if we just focus on 2D, and we have some barrier over here. This is true. This picture is symmetric, right? So we have M and we have A tilde of M. And this could be 2D or 3D. It cannot be 1D. In 1D, it is kind of flat, right? So it is flat. So the question for you now is, well, this was symmetric when there was no external magnetic field, right? Now, let's say you had a small external magnetic field, which was H more than 0. Do you still expect this to look symmetric, or do you expect it to look asymmetric? Huh? Which side should be deeper if H is more than 0? That goes back to the question that Alan answered, right? If H is more than 0, you prefer, if H was very, very large, you prefer all spins to align along H, right? So you're preferring the spins to be the same direction as H, right? So the right basin should be deeper, the positive magnetization. So if H was positive, it's going to look something like this. And don't worry about the relative difference between the red and black. What you should worry about is the difference between the two basins of the black, okay? So there was a slight delta E that makes the M more than 0 is slightly preferred if H more than 0. Okay? So now you do that experiment where you started with H more than 0 and you keep bringing the H down to 0, right? So as you do that, what will be the physical effect on this side of the curve? It will also start to go down, right? So you had introduced an asymmetry in the system, right? You had applied an external magnetic field, which was saying spins aligning along H more than 0 is preferred over spins being against it, right? So it's like, what analogy can I give you? You know, it's like, well, yeah, all of you are magnets and there's a big magnet outside, right? And so everyone is aligned along that magnet. Now, if that magnet was not there, you could be aligned either against it, you could be aligned in direction of it, right? But now I'm going to, so when the magnet was there, all of you being aligned along it had lower free energy relative to you being aligned against it, right? Now I slightly, a lower free energy for being aligned to in its direction means that this basin over here is deeper, right? That's the idea. And now when you turn this external magnetic field down, the asymmetry starts to disappear. The curves become more and more symmetric. You have a question?
Shouldn't the right, on the right side, the black line should be lower than the red?
I'm not comparing red to black.
Okay.
It doesn't matter, right? Free energy is only relative up to a scale. So you can shift the whole black, you can shift the whole red. We don't care about that. What we care about is the relative value of 2 points on red, right? So free energy is, this is A tilde M plus an unknown constant, which we call AF, standing for Alex Freeman. Okay, we don't care. We can scale that constant, right? It doesn't matter. It does not depend on delta M. So here's physically what goes on. In 2D, if you prepared your system starting with an external magnetic field that was positive, it will like to be over here, right? Because you're telling it, stay over here. And now when you turn the field down, suddenly everything becomes symmetric. So yes, as per probability, it should be left, it should be right. But there is a reason it cannot go to the left. What is the reason? There is a barrier in the middle. It has to surmount this barrier, right? As you go to 3D, the barrier becomes even higher. So you've prepared this system in a certain state, even though thermodynamic equilibrium tells you you should have an equal population of state, there is going to be a barrier. So if you wait long enough, it will equilibrate and you will get equal population. But as you go to 3D, you have to wait even longer. As you go to 1D, how long do you have to wait? You don't have to wait. There's no barrier. It will simply equilibrate, right? So what we have done is to prepare the system in a state of broken symmetry. System takes a state of broken symmetry. This is not an equilibrium state, right? It is kinetically stabilized, which is kinetically stabilized. And actually, this kinetically stabilization becomes, in thermodynamic limit, it becomes infinitely stabilized. Why? Because this barrier E star scales as n. So as you go to thermodynamic limit, the barrier becomes infinite. So if you prepare the system in one state, unless you are 1D, you are just going to get trapped, right? So this is how you can have magnetization. So the solution to our puzzle comes from kinetics. And in general, in most of the problems in chemical physics, physical chemistry, biophysics, if thermodynamics is not giving you the right answer, generally there is some kinetic factor which is under play. You think your system should take a certain state. You prepare some DNA molecule which you think should be left-handed or right-handed, but you're always finding it to be left-handed. So maybe there is some effect of how you prepared it, which is simply not going away, right? So that's why you have to be. So what would be the solution to this conundrum? How would we solve this conundrum eventually? So I showed you why it goes on. So if we really had to prepare the system in 2D with both populations, what should we do physically?
Minimize the external magnetic field. It's not just possible.
That won't do it because the barrier is still there. But yeah, something related to the external magnetic field. What should we do? Michaela, what do you think? Opposite direction, you get a chocolate. Because if you started with H more than 0, everything was getting trapped in the right-hand side basin. Well, you start with H less than 0 and everything will get trapped in the left side basin, right? And if you equally prepare your system, so what is it telling you? You have to think about, you can also have one, Aurelia, if you want. You just need to answer a question, or I can give you one. So, so this is and actually the barrier is not really proportional to n. In 1D, the barrier is proportional to n to the power 0, right? What is the origin of the barrier? The origin of the barrier is this surface, right, that you created. So in 1D, the surface is just 2 points. So there is no dependence on n. In 2D, how do you expect E star will depend on n? In 2D, what is the nature of the barrier? Is it a sphere or is it a circle? Circle. What is the circumference of the circle? How does it depend on the radius? What is the, well, you can think about it, but basically this will be n to the power half. And in 3D, it will be n to the power 2 by 3, but something expensive, right? Something that all of these things blow up as n tends to infinity, right? So this is the reason why you will get kinetically trapped if you're not careful in how you prepared your initial setup. And this is why I'm discussing this today, because more than half of you are experimentalists, right? You want to study some equilibrium property of your system. And if you don't prepare it the right way, if you're not careful about how you prepared it, you're screwed. You will not get equilibrium properties. You will get some kinetically trapped state and you will be wondering what's going on, okay? Any questions about this? Go ahead, Patrick.
Can you explain why changing the sign of the magnetic external field?
Yeah, so if H was more than 0, we had a population, we had a free energy that looked like this, right? If H was less than 0, we have a free energy that looks like this. So if H is more than 0, everything will come over here. If H is less than 0, everything will come over here in the arrows that I drew. So H less than 0 means you trap the system in the left basin. That's the idea, because it's favored for high enough H, right? And this is simply an effect of the fact that for high H, this term dominates in the microstate energy, right? That's where it's coming from. Okay, good. Any more questions? So in the remaining like 30, 40 minutes, I'm going to tell you about an idea that led to the Nobel Prize in 1978 or something like that to Ken Wilson. I will give you a basic flavor of the idea. I have posted an article by Leo Kadanoff. It's a really, really nice article that you should read, and hopefully you will get the basic idea of how it works. So this thing is called renormalization group. Why was this introduced? So renormalization group had existed in quantum mechanics since the 50s or 60s. Murray Gell-Mann, who some of you might know. Does anyone know why is Gell-Mann very famous? What did he discover? Chocolate, if you know. Don't look up on the internet, Alex. What did Gell-Mann discover for which he got the Nobel Prize? He theoretically predicted it, and then it was found in the lab many, many years later. No one knows? It starts with a Q. Quark. You want another chocolate? You're not giving it to him.
I'll give it to someone else.
Okay, here you go. You can have it. So Gell-Mann was the inventor of quark. Just come and take it. So, and he used to think about these renormalization group ideas in quantum field theory. And I think Gell-Mann's student was Ken Wilson. He was an undergrad at Caltech when he started thinking about these things in the 70s. But Ken Wilson, when he was a grad student at Harvard, he ran a sub 4-minute mile. I think that is the only Nobel laureate to have ever run a mile under 4 minutes. And back in the day, I think less than 100 people in the world could have run it that fast. It's kind of a record. So is there anyone here who has run like a sub 5-minute mile? Sub 6 minute?
6 minutes flat.
But you know how hard 4 is, right? To be a Nobel laureate who has done a sub 4-minute mile, it's like mind boggling. So Ken Wilson, together with Michael Fisher, who was a professor here, and Ben Widom, who is still a professor at Cornell. These 3 people, and also Leo Kardanoff, whose article I posted, these were the people who were really thinking about this ideas of renormalization group theory in the 70s and 80s. Somehow the Nobel Prize was only given to Ken Wilson, which I don't know why that is the case. The most famous paper on this is a paper together by Wilson and Fisher in PRL, which is called Ising model in 4 minus epsilon dimensions or 3 minus epsilon dimensions, something like that, right? So what were these people trying to do? They were trying to think about Ising model and related systems and trying to develop a formalism that can give them the critical temperature for any type of interaction in any dimension, right? Because we saw mean field theory got better and better in 2 limits, when the dimension became infinity or when the interactions became infinitely long range, right? So, but these people wanted to come up with a better idea, and they observed the structure of the of Ising models, and they came up with this idea. Michael Fisher did not get the Nobel Prize, but he did get the Wolf Prize, which is almost next to the Nobel Prize in physics. So the idea was quite physical. The idea was that let's think about a 2D Ising model, okay? So you have plus, minus, plus, minus, plus, 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 minus, 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 whatever, right? Some arrangement of spins, up, down, whatever you want to call it. So the idea was you could look at spin by spin at a time, right? But how about you look at blocks of spin at a time, right? So don't look at one spin at a time, but look at 4 spins at a time. So what is the maximum value 4 spins can take? Plus 4. What is the minimum value 4 spins can take? Minus 4, right? So it can be anywhere from minus 4 to plus 4. That's not an Ising model, that's a Potts model, right? But there is still some similarity, right? There is still a random variable which can fluctuate into some values. So they tried to come up with a framework which can kind of zoom out in a physical problem and see how the fundamental properties of a system vary with the scale of measurement. So for most systems, the fundamental properties will be very different on the scale of measurement, right? If you're measuring something at a nanometer scale, it's quantum mechanics. If you're measuring something at a light year scale, it's probably general relativity, right? So the physics changes, but there are a lot of physical systems where the physics actually does not change very much. The name for such systems is fractals, right? That's one of the names. They're also called as self-similar structures. So one of the best examples of a fractal is if you're in a plane, people say, I mean, actually people say that's the best example, but I really don't know how to do that because you will have to a plane that is really focused on the shore of a beach, right? On the beach, and you keep going on the beach. And the idea is that if you look at the beach from the sky or you look at the beach from closer, it still kind of looks the same, right? A better example is a snowflake. You can keep zooming into a snowflake and it still has that kind of a structure, right? A hexagonal structure. You can zoom in more and more and more. Does anyone else know of examples of fractals in real life? Trees, yeah, you have branches on a tree, right? You have branches going out and you go on a certain branch, again, there are branches going out, right? So anything else? Dendrites, You are a metallurgist, you know what's dendrite, right? When you cool something and it starts forming solid, it does not just make a beautiful solid structure. It actually looks like the branches of a tree. You have little structures, and how these things grow can have enormous effects on what else?
Rivers.
Huh?
Rivers.
Rivers. Why? Yeah, tributaries. Correct. Tributaries are like that. Neurons in the brain, right? If you think about it, there are always new neurons branching out, and you can think of. So that's why people use Ising models to model neurons in the brain. So we are going to make this a bit rigorous, and there are many ways of thinking about the renormation group approach. We are going to follow an approach that is described in the Kardanoff paper. So I posted an article online. It's by Kardanoff and some less famous scientist, I forget his name, in American Journal of Physics, C class webpage. I have provided PDF, and it goes over this, what I'm saying. So we are going to go through this idea of decimation. When you hear decimation, it sounds like destroying things, right? It's like, I'm going to decimate you. You're done. So what does decimation mean? Decimation means you remove certain degrees of freedom to have a smaller system. Okay, and we will start by looking at 1D. I will do more or less the full math in 1D. In 2D, I will not do the math. You will see why I won't do it. But the paper that I have written above, that does the math in 2D. And you will see how this shows you, first of all, a practical way to get the critical temperature in any dimension. And number two, it shows you why in 1D, similar to the pulse droplet idea, why is there no critical temperature? And we are going to think about first an Ising model in 1D with nearest neighbor interaction and H is equal to 0. Okay, no external magnetic field. So what is the energy of a microstate for this system? You go to every microstate. Here you will be interested only in microstates where modulus of I minus j is equal to 1, right? First nearest neighbors. And you do e to the power minus beta E nu. So if you have, no, what did I do? What did I write down? That's not E nu. That's something else. What is this something else? What did I write down over here? What is this thing? It's nothing actually. It's garbage. No, it's garbage. So Q, that's right, it's related to Q. So Q of the system at N and T, we are not talking about any volume here, right? That's something you should notice about Ising models. There is no notion of volume, right? You have a fixed lattice. Volume is kind of stuck. So Q of NT of this system is going to every microstate and then calculating e to the power minus beta E nu, right? What is the meaning of every microstate? That means you go to S1, S2, S3, S4, as many spins as you have, each of them can take plus minus 1, right? And then for any given configuration, you do e to the power minus beta E nu. So if you have only first nearest neighbors, we can define E nu, that will be minus modulus of I minus j is equal to 1, j si sj, right? So in order to follow Chandler's notation, Chandler also does this and Kardanoff also does this. I'm going to introduce a term that K is defined as beta multiplied by J, okay? So J divided by KBT. Why do I do this? Because I'm interested in minus beta E nu, right? So I'm going to multiply this J with beta all the time. So instead of writing beta J, I'm just going to call it K, okay? So if I have this, so let's call this equation number 1, this as equation number 1, this as equation number 2, this as equation number 3. So what becomes the value of Q? Now I can think of Q as N, comma K, right? Because temperature's role has been replaced by K, right? Temperature comes only through beta, and now we have K. So what is Q of N, comma K going to look like? We are going to every spin S1, S2, S3, Sn is equal to plus minus 1. And what should I have here? I should have plus K, right? Not beta J, but not minus beta J, but plus K. And then I'm going to have S1, S2 plus S2, S3 plus S3, S4 plus S4, S5 plus dot, dot, dot. Why did I not write S1, S3? Only first number interaction, right? So this is what we are going to look at. Let me write it down on the next page, the same equation. So Q of Nk is going to be S1, S2, S3, Sn equal to plus minus 1. And you have e to the power plus k, S1, S2 plus S2, S3 plus S3, S4. And k is equal to beta j. Does anyone know, apart from Suimin, who is Eric? It was talk in my group, Eric Bearley, doesn't Patrick knows him. So you were talking about 6 minute mile, right? So this guy is a competitive runner. He just ran a half marathon on Sunday, which is 13 miles, and his average pace was 5:12. So he came 13th in 3,000 people. You can see him. He's like the skinniest person in all of IPST. He just walks around like a stick. He's really, really fast. His PR is 4:12 in a mile. So this one. So now we cannot calculate this. This is a mess, right? Is there any hope of doing this explicitly? It's terrible, right? How many terms do we have in this summation? Chocolate. Huh? Swimming, what do you think? We have n spins, and every spin can take 2 values. So how many terms do we have? 2 to the power n? Is it 2 to the power n, or is it 2n? Or is it n choose 2? You have to pick. Only Swimming. Which one? No, think harder. Chocolate is at stake. Why? That's one answer. No, this is something simple, but let's think about it carefully. So if we had 3 spins, S1, S2, S3, and everything can take plus minus 1 value. Let's try to write down. Can you tell me what value should I have? Let's try writing it down explicitly. 1, 1, 1, then 1, 1, minus 1, then 1, minus 1, 1, 1, minus 1, minus 1, then minus 1, 1, 1, minus 1, 1, minus 1, then minus 1, minus 1, 1, minus 1, minus 1, minus 1. Right? This is, so how many values did you get? 8, right? So 2 to the power 3. Here's the chocolate. You can come and take it. So for n spins, we get 2 to the power n combinations, right? So it's a hugely complicated sum where you have 2 to the power n terms, and each term you have to go and calculate this thing, right? So for this one, you can calculate S1, S2 plus S2, S3. The value is 3, right? So you have to do this math again and again and again. It's going to be terrible. So that's not going to really work. I'm going to just erase this part because I want to write on this page. So here comes the renormation group idea. The idea is to remove or decimate even spins. So you average out over even spins. So what does that mean? Let's look at it carefully. And we are thinking only about 1D, right? So we had spins that look like 1, 2, 3, 4, 5, 6. So we are going to remove spin number 2. We are going to remove spin number 4. We are going to remove spin number 6. What does it mean? We cannot just pluck it out, right? It's there in the system. It's like I'm trying to model you all as an Ising model and I just remove people at time. No, but I can average over the behavior of people in like even positions, right? That's what I'm going to do. In order to do this, I'm going to look at, and this equation I'm going to call equation number 4, and I'm going to write equation number 4 in a slightly different manner. I'm going to write it as Q and K summation, once again, S1, S2, S3 is equal to plus minus 1 e to the power K S1, S2 plus S2, S3 multiplied by e to the power K S2, S3, S4 plus S4, S5 multiplied by e to the power k S5, S6 plus S6, S7. Everyone happy with this? I've just taken, everything is coming one time, right? S1, S2, S2, S3, but I've removed it in a separate direction. But notice something interesting that has happened. S2 shows up only here, right? S4 shows up only here. S6 shows up only here, right? So now we can do something interesting, is to think about this summation in two different parts, okay? We will write it as summation over S1, S3, S5, S7 going to plus minus 1, and an inner summation of S2, S4, S6 going to plus minus 1, okay? And then we will keep everything the same. K of S1, S2 plus S2, S3 e to the power k of S3, S4 plus S4, S5 e to the power k of S5, S6 plus S6, S7 dot dot dot. Okay. So far I haven't done anything except just like move. It's like moving money from one pocket to another pocket, right? I've not done anything profound or anything interesting. Now I will do something interesting. I can make the summation even cleaner. I have this, no, I don't want to erase. I have this complicated sum, which has S2, S4, S6, everything. But there is only one term that depends on S2. That is this one over here, right? There is only one term that depends on S4. That is this term over here. So I can simplify this even more, and I can write it as S1, S3, S5 summation over S2 e to the power k of S1, S2 plus S2, S3 summation over S4 e to the power k S3, S4 plus S4, S5 dot dot dot, right? And this summation is going to be complicated. This summation, when you do it, this summation has S1, S2, and S3, right? And you're summing over S2. So what are the things that will disappear? S2, S1 and S3 will still persist, right? So what values can S2 take? Plus minus 1. What value can S4 take? Plus minus 1, right? So actually, let's do the summation and let's see how it looks like. Then it's going to look like that I have only a sum over S1, S3, S5, right? And how does the summation look like? That's going to look like a to the power k. If S2 is equal to 1 plus 1, what is the value of S1, S2 plus S2, S3? That is S1 plus S3, right? So e to the power k S1 plus S3 plus e to the power minus k S1 plus S3, right? What will be the second term due to S4? E to the power k what? S3 plus S5 plus e to the power minus k S3 plus S5, right? And you will have other terms like this. And you can see this has only S1 and S3. This one has only S3 and S5. So something is starting to happen. This is not an Ising model. It looks very complicated. But we have removed all the S2s and S4, right? They are gone. They have been averaged out. So let me write down that equation once again. So we just showed, and I will call it equation number 5. I will write down equation number 4 once again because we are going to use it. So equation number 4 was going to every spin S1, S2, S3, and then doing e to the power plus k S1, S2 plus S2, S3 plus S3, S4, so on and so forth. And that was equation number 4. And equation number 5 is Q of nk. Now we have summation only over S1, S3, S5, S7. We have gotten rid of S2, S4, S6. And it looks a bit different. If you remember, it looks like e to the power k S1 plus S3 plus e to the power minus k S1 plus S3, right? Multiplied by e to the power k S3 plus S5 plus e to the power minus k S3 plus S5, so on and so forth, right? So what is the problem in this equation? The problem is that this S3 shows up in both terms, right? If you had S1, S3 in the first square bracket, and if you had S5, S7 in the second square bracket, then that would be kind of nice. That would be like, oh, it's independent, right? S1, S3 only talk to each other. S5, S7 only talk to each other, right? Life would be very simple. But it's a bit complicated. Let's call this equation number 5. But what Kardanoff and others realized is maybe there is hope. Maybe there is a possibility that equation 4 and equation 5 for certain type of physics are very similar. What do I mean by that? What I mean by that is if e to the power k s plus s prime, by s plus s prime, what do I mean? It could be s1, s3, s3, s5, whatever you want, plus e to the power minus k s plus s prime is equal to some function of k multiplied by e to the power k prime s s prime. We call this equation number 6, I suppose. If this is true, and we have to think about it, we will come back to this equation. This is the key equation that we're going to solve. It looks very messy, but let's try to develop intuition as to why such an equation matters. If this was true, if you put equation 6 in equation 5, then see what equation 5 will look like, right? If we could have, before I do that, let's see why this is a big leap of faith. In this equation, how many unknowns do we have? K is known, right? K prime is not unknown, and this function f is not known, right? So 2 unknowns. So 2 unknowns, f of k and k prime. Can you solve for 2 unknowns from one equation? You cannot. That will be terrible. Well, it will be awesome, but it's not going to happen. But do you have only one equation, or do you have more than one equation? We have 4 equations. This has to be true for s prime equal to plus minus 1, right? So you can write down this equation for s equal to plus 1, s prime equal to plus 1, s equal to minus 1, s prime is equal to minus 1. Now you have opposite problem. You have 2 unknowns and 4 equations. That's also not good, right? So we are kind of screwed. Turns out that 2 of the equations are the same. So we can actually solve for it, and it will be 2 equations in 2 unknowns, and we can get the value of this function, and we can get the value of k prime. But why should we do that? Why is that worth doing? For that, we have to put 6 in 5. Equation number 5. If you put 6 in 5, what's q of nk going to look like? Notice something very interesting will happen now. S1, S3, S5, S7. So e to the power k s plus s prime plus e to the power minus k s plus s prime is equal to function of k multiplied by this thing. So every square bracket is going to contribute 1 f of k, right? How many square brackets do we have? Chocolate. Huh? N by 2. Yeah, you got a chocolate dark. Is everyone happy with n by 2? Because we removed half the spins, right? So we have n by 2 brackets. So what do we mean for, sorry for making you walk, but if I threw it, it can become like a pulp. Oh, I have a story about these chocolates. I should tell you. I won't get the chance to tell you stories anymore. So my grandfather is very, very old. He's like 93 years old. So there was a point he did not have any teeth. So he used to love this chocolate because it does not require any teeth, right? You can just. So I took it to India, and I went to this place called Bhabha Ethnic Research Center in Bombay. I had to give a talk there, and they have a lot of monkeys. So I was a postdoc in Switzerland then, so I bought like big box of this, and I left it in my room and left the window open, and I come back in 2 hours, everything was gone. The monkeys had taken everything. So monkeys are very mean. So every spin, every pair, every box contributes f of k, right? So we have f of k to the power n by 2. But now we have to think about this one. What's that going to be? That's going to be e to the power k prime. What is S now? That is S1, right? And what is S prime? That is S3, right? How about this term? What is that going to be? E to the power k prime S3 S5, right? Does f of k to the power n by 2 depend on the value of spins? It's just a number, right? There is no spin there. It depends on k, but it does not depend on spin. So suddenly we have a very beautiful structure that has emerged. Q of nk is equal to f of k to the power n by 2 summation S1, S3, S5, S7 e to the power k prime S1, S3 plus S3, S5 plus S5, S7 plus dot, dot, dot. Let's call it equation 7. Equation 7 is just like equation 4, isn't it? Right? Where spin number 1 talks to spin number 3, spin number 3 talks to spin number 5, spin number 5 talks to spin number 7. You have a different prefactor, but we don't care about prefactors, right? Why don't we care about prefactors? Because in order to get thermodynamics, we will look at log of Q, right? And the prefactor will just drop out in the log when you differentiate it and things like that. It won't matter. So if we could solve equation 6, where we had 4 equations and 2 unknowns, then you will see that this actually becomes 2 equations. Then we have a way to take the Ising model for n spins and map it into an Ising model for n by 2 spins. This is not entirely useful, right? Because n is a large number and you have just changed to n to n by 2. But what's stopping you from changing n by 2 to n by 4? You could keep reducing it until it becomes 1 spin. And you can solve Ising model for 1 spin. That is kind of trivial. That's one thing you can do. What we are going to do is something different. You will see that this amounts to turning down the interaction. This amounts to removing the j from some finite value to j is equal to 0. And we know how to solve Ising model for j is equal to 0. As Swayman told us, there are 2 to the power n microstates. And if you have j is equal to 0, they are all independent, right? It's totally simple. So let me show you how that works. For that, we have to solve. I'm not going to finish this today. It will need some more time on Tuesday. So on Tuesday, it will probably need 15, 20 minutes, and then I will do a recap. I will stop in 5 minutes, and then I will pick it up from there on Tuesday. And I recommend please going at least briefly through the Kadanoff paper. That will help if you are interested in learning about reevaluation group. If you are not, then that's okay. It's not going to be on the exam. So what we need to do is to solve equation 6 for all values of s and s prime, right? So equation 6 was e to the power k s plus s prime plus e to the power minus k s plus s prime is equal to some f of k e to the power. And how they came up with this is kind of magical, because I guess, yeah, it is. I could not have come up with this on my own, that they saw something like this could be done. E to the power k s s prime. So if s is equal to s prime is equal to plus 1, right? We have to do 4 equations now. What's this going to be? E to the power 2k plus e to the power minus 2k is equal to f of k e to the power k, right? That's equation number 1. What is the next one? S is equal to s prime is equal to minus 1, right? What equation do we get? E to the power minus 2k plus e to the power 2k is equal to f of k e to the power k. Did we get a new equation? Got the same equation, right? So far we have only one equation, this one. Let's call it equation 8a. Now we have 2 more things. S is equal to minus s prime is equal to plus 1, right? So s is equal to plus 1 and s prime is equal to minus 1. In this case, what will you get? What is s plus s prime now? E to the power 0. What is minus s plus s prime? 0. And what is that equal to? F of k to the power minus k, right? And the final condition where s is equal to minus s prime is equal to minus 1, same thing, right? E to the power 0 plus e to the power 0 is equal to f of k e to the power minus k. Oh, I made a mistake. Does anyone notice? This is k prime, it's not k. This thing is k prime. F of k multiplied by e to the power k prime. I have been in deep trouble. So what does this become? This becomes f of k e to the power minus k prime is equal to 2. That's equation number 8b. So we have two variables, f of k and k prime, two variables and two equations, right? So we can solve for it. How do we solve for it? So 8b, this is just algebra, the following lines. So f of k is equal to 2 to the power e k prime, right? I just moved e to the power minus k prime to the right side. So put this in 8a. So we have f of k is equal to 2 e k prime, and the left-hand side of 8k, so the right-hand side of 8k will become 2 ek prime multiplied by ek prime, right? So 2 e 2k prime. The left-hand side is e to the power 2k plus e to the power minus 2k. That can be written using a hyperbolic function. Anyone remembers? We saw hyperbolic tan last time. This one is related to hyperbolic cos, okay? So this one becomes 2 hyperbolic cos, and when I say this one, what do I mean? I'm thinking of this thing, right? So this thing becomes 2 hyperbolic cos of 2k. So what do I get? I get hyperbolic cos of 2k is equal to e to the power 2k prime, or log of hyperbolic cos of 2k is equal to 2k prime. So we know how to get k prime from k now, right? It's a complicated mathematical quantity, but we know how to get it, right? Remember, so again, there is no way that most of you are not lost at this point in the algebra because it is messy. But just to remind you, how did we get with k? K was beta j, right? That's what we had it. So we knew the interaction j, we knew the temperature that we were interested in, and we just showed that k prime is equal to 1/2 ln of hyperbolic cos of 2k, right? Let's call this equation 9a. And now we can write f of k, because we know f of k is equal to 2 e to the power k prime, right? So we know that function also. So f of k is equal to 2 square root hyperbolic cos of 2k. So this is magical, what we have been able to do here. We have been able to take an Ising model, remove half the spins, every alternate spin, and map it into another Ising model with half the number of spins, with a different prefactor, the f of k to the power n by 2, and a different interaction term that depends on the first interaction term and its temperature of that system, right? So this is how it looks like. In other words, what we have shown is that q of n comma k is equal to f of k to the power n by 2 summation s1, s3, s5 dot 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 e to the power k prime s1, s3 plus s3, s5 plus s5, s7 I'm going to finish in 2 minutes. So this thing can be written as q of n comma k, right? It's a partition function that depends on n and k multiplied by f of k to the power n by 2. And what is this thing? This is a partition function that depends on n by 2, right? Because half the spins are gone, they have been removed, comma k prime, right? In math, when you have a relation between f of x and f of x minus 1, and you have to solve for f, such an equation has a name. Anyone remembers? It's a recursion. It's a recursive equation. You have a recursive equation here, where now we can take the log of both sides, because in the end we are interested in free energy. So ln q of nk is equal to half n ln f of k. So this, by the way, is a recursion relation, and we are going to simplify it for free energy. Again, this is not an exam, so just get the big picture of why this is so. Hopefully you can see why this is beautiful. So ln q of n by 2 comma k prime, right? We will introduce a free energy that is intensive and depends on k. Okay, so this free energy is defined as it's free energies in quote. Okay, we are not worrying about beta and things like that, but you get the spirit of it. So this is ln of q of nk divided by n. Okay, this is my intensive free energy in quotes. So this equation 10 becomes, if you divide by n both sides, right, it will become g of k is equal to half ln f of k. No, g of k is equal to, yeah, half ln f of k plus half g of k prime, right? Or finally, we have g of k prime is equal to 2g of k minus ln of 2 square root of hyperbolic cos of 2k. And this is known as the central RG equation, the central renormalization group equation. It's got a name central, so it must be very important, right? Do you see what's going on here? You have a system with a certain interaction K, right? K means, once again, beta and J. You know the temperature, you know the interaction energy. If you can solve for the free energy of that system, get it G of K, ln of 2 of square root of hyperbolic cos of 2k, even though it looks messy, it's just a number, right? You take the hyperbolic cos of 2k, you take its square root, multiply by 2, take its log. You get the free energy of something else, right? So it allows you to move across scales. It allows you to connect the free energy of a system with k, with a free energy of a system with k prime. So I'm going to stop here. Next time, I will start with this equation and show you how it actually works. What we are going to do is to start with a k prime, which is very, very small, and keep increasing in k. K prime, very, very small, is trivial to solve. The partition function is just 2 to the power n. That's it. And we'll start from there. Yeah, go ahead, okay?
What is the 1/2 on the GK?
Oh, I just multiplied. I did a bunch of algebra. Sneaky algebra. Okay, so go through Kadanoff's paper. He does everything. Chandra also does this. So please come to class on Tuesday. I will do a recap of the semester. And but I will also finish off this stuff.